Welcome to the third and last part of Chapter 6. So Chapter 6 ends with a brief discussion of polarization transfer. In fact, this expression inept means insensitive nuclei enhanced by polarization transfer. This is typical of so-called acronyms, that is to say, short words that are made up of the initial letters of a long expression, and this has become very popular, a fashion that was started by my PhD advisor Ray Freeman and has since taken over the entire world of NMR. It's full of acronyms that you may wish to remember, or some of them you may better forget. Now, inept is an idea that is applicable to heteronuclear systems with protons and carbon-13 or perhaps nitrogen-15 or some other funny nuclei. And the idea is that the inherent sensitivity of the protons is better than the inherent sensitivity of the carbons because the protons have a higher gyromagnetic ratio. And the basic idea is to apply a pulse sequence which starts by exciting proton magnetization, then allowing that to refocus by forming this echo, and at the top of the echo apply a pair of pulses which have the net effect of transferring the transverse magnetization from the protons to the carbons, and this corresponds to a gain in the amplitude of the carbon spectra. So to understand why one should like to apply inept to a heteronuclear system, we first have to look at the populations in thermal equilibrium, according to Boltzmann's law. The idea is that in Boltzmann's law, the differences in population are proportional to the difference in energy. So the carbon transition here has a small splitting, and consequently if we have 6 balls here, that means the most populated state is the ground state, and only 5 balls here, there's a difference of 6 minus 5 is equal to plus 1. Whereas if we look at the proton transition here, we have a difference between 6 minus 2, which is 4, and consequently the difference in populations is 4 times larger across the proton transition than across the carbon transition. Likewise, we have plus 1 here and plus 4 here, so this distribution here with these little balls represents a Boltzmann distribution. And it's immediately obvious that this is unfavorable for the carbons and favors the proton transitions. Now the idea is that the inept will reorganize the populations in such a way that the proton transitions will become antiphase, so one will be plus 4 and the other will be minus 4, whereas the carbon transitions will be considerably amplified. Instead of plus 1 we have minus 5 here, and then instead of plus 3 we have plus 3 here as a difference in population. So this is achieved, as you can see, by swapping populations. For example, the 2 balls here end up here and the single ball here ends up down here. And this can be achieved with the pulse sequence that you see here. We note in passing that in this case, if we consider the doublet of the carbons, we have a positive polarization of 3 units and a negative signal of minus 5 units. But if we then add a normal carbon spectrum on top of that, then we have 3 plus 1 is equal to plus 4, and minus 5 plus 1 is minus 4. So this restores a symmetry. This is not symmetrical, not antisymmetrical, but this is now perfectly antisymmetrical, and indeed that is one of the things we can do. In practice, we do that by alternating the phase of this pulse here. It turns out that the inept experiment can be explained in terms of semi-classical magnetization vectors. That means that, in fact, we associate a magnetization vector m with each and every single quantum transition. In other words, that if we have a pair of energy levels, we consider that as a so-called fictitious spin 1/2, and we assume that we can associate a magnetization vector with each of these transitions. In fact, it turns out that a more powerful way of looking at these things is in terms of density operators, and more specifically in terms of product operators that will not be discussed in this book, but are the subject of the next volume in Peter Hoare's series. But if we consider semi-classical vectors, then in the thermal equilibrium we have in fact not one but two proton vectors corresponding to the two parallel transitions, and they are both aligned with a magnetic field. We start by applying a 90-degree pulse around the x-axis, and we find that the two proton vectors are flipped over along the minus y-axis, as you would expect. Then we wait for a delay. This delay tau is in fact 1 over 4j. That's the coupling, the scalar coupling between the carbon-13 and the attached proton. And after that, it turns out that these vectors will have precessed in this interval through different angles like this. So one of them goes all the way to this position here, that is in great hurry and runs quite quickly. The other one only has gone through a small phase difference. At that point, we can apply a 180-degree pulse to the protons, and the net effect of that is to rotate, to flip the pancake, as Erwin Hahn would have said, and cause the proton vector H alpha to end up in a symmetrical position with respect to the ZOX plane. And likewise, the beta vector ends up in a symmetrical position to where it was before this pulse. The next thing we have to do is apply a 180-degree pulse to the carbon-13. And the net effect of that is simply to swap the labels of H beta to H alpha, and H alpha becomes H beta. If we did not do that, then the echo would form and there would be no refocusing, there would be no effect of a scalar coupling. But because we have done that, it turns out that the two vectors will continue to diverge, and the H alpha vector will end up along the plus axis, whereas the beta vector will be ending up along the minus x axis. Now, at that point, we have two vectors in opposite sign in terms of density operators. We would say that we have an AX carbon Z, and at this point here, so this is point F, so that makes the connections with the more sophisticated density operator, or we can also call this, in fact it should have a norm in front of it, and this could be called IX for the proton and SZ for the carbon. Now at this point we're going to apply the 90-degree pulse along Y, so we simply rotate through 90 degree around this axis, the net effect being that the H alpha vector goes to the south pole, whereas the H beta vector returns to the north pole, in fact to the same position where we started off. So the overall effect from here to here is simply to invert the magnetization of the H alpha line while leaving the magnetization of the H beta line intact. But the reason why we do all this is that we can achieve that effect for different chemical shifts. So it works for all multiplets, for all doublets at the same time. Now this position here can be described, so the position G can be described in terms of density operators as a HZCZ term, or if you prefer, an IZ for the protons and an SZ for the carbons. This is also known as a distribution of populations called longitudinal two-spin order. It turns out that we can consider the proton transitions, but we can also consider the carbon transitions that correspond to this state. And then we can apply another pulse, this time along the x-axis, to flip the carbon magnetization down to the minus y-axis, and at the same time flip the C alpha magnetization along the plus y-axis. Now, there are many interesting experiments that go together under the expression of two-dimensional NMR, which we like to call simply 2D NMR. And in fact, two-dimensional spectra have two distinct frequency domains, omega 1 and omega 2. It turns out that they can be obtained by recording a signal in time domain with two distinct variables, T1 and T2, and that we can apply a Fourier transform to T1 to generate omega 1 and to T2 to generate omega 2. But we shall not go into any details on how this is actually recorded, but just note that in general we have to decide on some preparation technique. In the simplest case, this might be a 90-degree pulse, like in INEPT, for example. Then we have a period in which there is usually no perturbation at all, where we allow the spins to evolve freely. And then we need some sort of a mixing interval. It could be a simple 90-degree pulse before we detect the signal. So it turns out that the simplest realization is this 90 T1 90, and this is known as COSY, or also correlation spectroscopy. And you may wonder what this is good for. Well, it turns out that a COSY spectrum for a two-spin system looks like this. So the single quantum ordinary 1D spectrum has simply two doublets, one centered on the chemical shift of spin A, the other centered on the chemical shift of spin X, both split by 2 pi j if we use units of radians per second. And it turns out that the resulting two-dimensional spectrum has a diagonal about which it is symmetrical. There are multiplets here that are known as diagonal multiplets that we shall not look at in great detail, but more importantly there are these off-diagonal multiplets which tell us that the multiplet here centered at X is actually connected with a multiplet centered at A. So the existence of this multiplet here, this is considered as the proof that JAX is different from 0. So whenever we see a multiplet here, we can say, aha, there must be a coupling. And that is very important for the assignment and in many applications of chemistry. Actually, the spectrum that you see here, all the multiplets are in phase. This is not achieved by such a simple technique, but this is achieved by a more sophisticated technique known as total correlation spectroscopy, or TOCSY. We can also write that down. As you can see that acronyms are flourishing, and it turns out that the basic idea here is to do some longer mixing period between T1 and T2, which allows one to get in-phase signals rather than anti-phase signals. So the two simplest experiments that we can do by two-dimensional NMR are the COSY experiment, which really means correlation spectroscopy. Maybe you should write it out. Correlation spectroscopy. And it's actually not a good acronym because it uses the first and the second, this first and the last letter here, but it's a nice word. It was popularized by Kurt Wüthrich at ETH and has been now widely accepted. And the other experiment would be nuclear Overhauser effect spectroscopy, the same idea. You can also write the last Y with a capital to make it plain that those belong to these two letters. And these are the two basic experiments that are most routinely done. Now it turns out that in the COSY experiment we simply apply a 90-degree pulse to excite transverse magnetization, which will then evolve under the effect of its chemical shifts and J couplings. But we choose not to look at the magnetization. We do not put the free induction decay in the computer. We just ignore the signal and apply a 90-degree pulse which converts that transverse magnetization into transverse magnetization of connected transitions. The NOSY experiment is built on a different principle. Here we also have the same idea of a precession of transverse magnetization, but in this period here we have longitudinal magnetization of, for example, spin A. And the idea is that in this period here, because of Overhauser effect, the magnetization will partly travel spontaneously from spin A to spin X, and as a result, when it arrives here, the transverse magnetization will oscillate at the characteristic frequencies, the chemical shift here of spin X. So here we have a multiplet centered on the frequency of spin X, whereas here we have a multiplet centered on the frequency of spin A. So the COSY experiment is normally used for homonuclear systems, so we can consider our familiar energy level diagram for the two-spin system. And the magnetization that we initially excite would be here in these two parallel allowed single quantum transitions. And the idea of this 90-degree pulse is that they can be converted into transverse magnetization of these two transitions. And this conversion actually goes from here to here and from here to here. You can argue whether that actually goes through the populations or not, but the Bostic effect can be described beautifully with somewhat more advanced methods. In the NMR experiment, it's a slightly different situation. Here we have again a homonuclear case. So we have again magnetization, transverse magnetization in these two parallel transitions, and the net effect here is to convert that into population of these levels and then allow the NMR effect, that is the W0 flip-flop of the two spins, to connect the central populations of the central energy levels. And then from those central energy levels we can generate the transverse magnetization of these connected transitions. So there are many applications of COSY, or homonuclear correlation spectroscopy. We can apply COSY to proton spectra of molecules such as this. This molecule here was chosen possibly because it has many almost degenerate protons. In fact, it's a bit like a sugar, since we always have carbons with one OH and one H attached. And indeed, sugars represent a particular challenge because the chemical shifts are very close and it's not so easy to identify coupled neighbors. Sugar chemistry has greatly benefited from the invention of COSY. Now, we don't actually see the molecule, but what we can determine from the two-dimensional spectrum is a diagram such as this, which actually represents the topology of the coupling network. That means specifically that proton D is coupled to proton F and to proton I, F is coupled to D and I is coupled to B is coupled to A, etc. And this we can immediately determine by looking at the spectrum, for example, between the chemical shift of A and B, so the protons are here, the proton A and the proton B are up there. So we see a cross-peak here, and this cross-peak in fact corresponds to the fact that there is a scalar coupling between A and B. But we could also look at proton H, which is somewhere over here, and we see another cross-peak here, and that other cross-peak corresponds to this bar here, so those represent the J couplings. And it turns out that with the help of the COSY spectra and the determination of the coupling network topology, one can very often draw immediate conclusions as to the nature and the structure and the connectivity of the network of the protons in the molecule. Homonuclear correlation spectroscopy is often applied to protons, but it can also be applied to exotic nuclei, such as boron-11, which actually has a spin quantum number with 3 halves, and therefore it's a quadrupolar nucleus, and therefore the transverse relaxation is very efficient, the lines become broad, and the multiplets are not easy to detect in one-dimensional boron spectra. But it turns out that if we consider a cage such as this, or a half-open cage rather, we can immediately record COSY spectra and find that there are in fact off-diagonal peaks such as this one, which obviously connect boron in the 4 position and boron in the 3 position, and so this corresponds to a J coupling between 3 and 4. We find the same J coupling here, those are degenerate, and turns out that the interpretation of the spectrum allows us to reconstitute or to predict what the cage was, or determine what the cage is. So nuclear Overhauser effect spectroscopy is now a very popular method. But in fact, when it was invented, it was first applied to a problem that has nothing to do with Overhauser effects, but has to do with chemical exchange. And in fact, in its early version, NOESY was called EXI, which stands for exchange spectroscopy. And this is a beautiful example of how exchange spectroscopy can be used to investigate relaxation mechanisms or rearrangement mechanisms. This is a beautiful example that shows how exchange spectroscopy can be used to explore rearrangement mechanisms. This is a heptabenzylbenzononium molecule where there is in fact one CH3 plus methyl group in excess, and it doesn't quite know where to go, and therefore it travels around the ring. Now it turns out that this methyl group here hops from the 1 position to the ortho position next door, then the proton that is on the protons that are attached to the methyl group that stays behind will move from this crowded environment into a different environment, which is in the ortho position with respect to the new crowded environment. So you would expect the chemical shift of the methyl protons 1 to be different from the chemical shifts of the methyl protons in position 2. And indeed, if we look at the spectrum, we identify the proton chemical shifts of these two methyl protons. So this is the crowded and this is the ortho position, and we find here a cross peak, which is indicative of the fact that this group here has indeed shifted from the so-called 1-2 shift from one position to the other. It turns out that the pulse sequence that was originally invented to monitor exchange phenomena can also be applied to monitor Overhauser effects in homonuclear systems. So recall that in a large molecule, the Overhauser effect comes primarily from the flip-flop transition probabilities that we called W0 AX between the two up-down and down-up positions of the spins. And we also know that this W0 flip-flop probability is proportional to the inverse of the 6th power of the distance between the two spins. And consequently, if these spins are far apart, the 6th power will be a very large number and the flip-flop rate will be vanishingly short. Conversely, only when this R is in the vicinity of 3, 4, 5 angstrom can we actually expect to see a significant flip-flop rate. And it turns out that if we do a nosy spectrum of a large protein, typically a protein is composed of amino acids, and an amino acid might have up to about 10 protons or so. So if a protein comprises 100 amino acids, we would have about 1,000 protons. And indeed here along the diagonal, we would expect to see about 1,000 distinct chemical shifts of 1,000 different protons. Not all of them are connected, but if we take a little peak like here, we can immediately come to the conclusion that that peak must be at the intersection of two chemical shifts, for example, A here and X here, and the amplitude of that peak is directly proportional to the flip-flop rate, the W0 of the pair A and X, and therefore the amplitude of this peak is actually proportional to the inverse of the 6th power of that distance. So any one of these peaks tells you that these come close, so we come to the conclusion that if we draw a molecule as a loose chain like this, that A and X must be somehow close in space. And you can see from this 2D nosy spectrum that in fact there are hundreds or even thousands of little cross peaks here, and therefore we have thousands of restraints that allow us to determine the three-dimensional structure of the protein. This is quite remarkable because the protein is in solution. The solution is isotropic and homogeneous, so there's no need to make any crystals. There's no need to go to a synchrotron to look at X-ray diffraction patterns. We can do all this in solution. Now, HSQC is another barbarian expression. It means heteronuclear single quantum correlation spectroscopy. And in fact, what it means is that it allows you to correlate the spectra of gamma of protons which have a high gyromagnetic ratio gamma with other nuclei such as nitrogen-15 or possibly also carbon-13 that have a lower gyromagnetic ratio. The first part of it is simply the same, identically the same as inept. So we find inept here. So if you return to that page, you will see what that means. And then we have an evolution here of the nitrogen-15 magnetization until we apply another pulse. And in fact, it turns out that if we add another pulse here, then we have here exactly the same sequence. This is actually can be considered as retro-inept. And in fact, if we summarize what happened with inept, in fact, we were converting the transverse magnetization from the protons to the nitrogen. And what we do here is we convert the magnetization from the nitrogen to the protons. This little pulse here I've added simply for the sake of symmetry. This could be the symmetrical position of this, a 90x. So this would be a 90x. And then immediately after that we have a 90 minus x. So the sum of the two actually vanishes, no operation. And this is simply a trick in order to see the symmetry of the sequence between the inept and the retro-inept. The important result of this is that we get a map where we can correlate the chemical shifts of protons on the one hand and correlate the chemical shifts of the nitrogens on the other hand. And you see there are many little peaks in this map, and each peak corresponds to the polarization being transferred from an amide proton in a protein. We have this kind of situation here. So this is the beginning of a protein, goes on and on and on. And what we see here is a correlation between the chemical shifts of the amide proton and the amide nitrogen. And of course there are as many such groups as we have amino acids. In fact, one way of counting the number of amino acids is simply counting the number of peaks in the spectrum. It turns out that this pattern is very sensitive to the environment, and therefore we call this a fingerprint of the protein. And the implication is, and that is correct, that there are no two different proteins will necessarily have different fingerprints and therefore can be recognized as such. It turns out that such HSQC spectra can be used in drug screening, because if we take a protein and we combine it with a ligand that has some affinity for this protein, then we'll have a protein-ligand complex. In fact, the affinity will be described by a dissociation constant, which would be simply the product of the concentration of the free protein and the free ligand divided by the concentration of the complex. And one of the issues in drug research is to find a ligand that has a very small dissociation constant, maybe as small as nanomole per liter. Now, in doing this kind of research, it turns out that we can do a titration where we observe the protein spectrum, the HSQC spectrum of the protein, and titrate the ligand. And if we do that, then we will see that if we increase gradually the concentration of the ligand, that peaks such as this will move. In fact, we can see them move around in space, and we can map that motion. So if there's no ligand, we have some chemical shift, and then when the ligand comes in, we have a change in chemical shift. So this is a change in chemical shift. In the absence of ligand, we have the pure protein. When it's saturated with ligand, we have only the complex, and in between we have this sigmoid curve. And you can imagine, like with the pH titration, that this inflection point informs us of the stability of the complex. In other words, very stable protein-ligand complexes would do something like that, and very fragile ones would something like that. And the job of the pharmaceutical industry could be summed up by saying that you go from a bad ligand to a good ligand, a non-specific to a specific, a weakly binding to a strongly binding ligand. Now, there are many experiments that are built on the principle of combining two two-dimensional experiments in order to obtain one three-dimensional experiment. All of them have this idea that you start with a two-dimensional experiment that somehow achieves a useful purpose, and that would have a preparation, an evolution, a mixing, and a detection period. And then you take another experiment which has its own preparation, evolution, mixing, and detection, and you simply remove the detection period of the first experiment, and you remove the preparation of the second experiment, and you stitch them together. As a result, you get then sequence A, where you have a preparation, a first evolution, a first mixing, a second evolution, and a second mixing, and then you detect the signal at the end. Typical example, this could be an HSQC that would combine, for example, protons and 15, and then we know that we go back to protons, and then we can do a nosy after that, and that would be combining protons and protons. So that would be an HSQC/nosy experiment. Now, it turns out that there are many such combinations, and they can be used for all sorts of purposes. One important idea is to assign the spectra of proteins, and there is a particular challenge here. Now, this is just one application. There are many other applications in proteins. For example, if we would like to assign the proteins, we could do things like this. We could go from the amide proton to the amide nitrogen. Then we do a transfer to the alpha carbon here, and we could go to the beta carbon in the side chain, and we could do a transfer here and a transfer here and a transfer here, and then come back to this and end up here. So this is already 6 consecutive transfers, and that would actually allow us to correlate the proton of the amide group with the beta carbon in the side chain. These are typical experiments that are currently being developed in order to assign and interpret spectra, carbon, proton, nitrogen spectra of large molecular assemblies. So let's try to summarize the main features of Chapter 6 dedicated to experimental methods. First of all, the vector model turns out to provide a simple picture of many elementary NMR experiments. The vector model can be used to describe the effects of radiofrequency pulses, of periods of free precession, and above all of spin relaxation, that is to say, the return of the magnetization vector to its equilibrium position. The rotating frame is a crucial simplifying feature of the vector model. NMR spectra can be obtained by applying a Fourier transformation to the free induction decays, so that one transforms from time domain into frequency domain. Spin-spin or transverse relaxation corresponds to a loss of phase coherence. T1 and T2 can be measured using either inversion recovery or spin-echo pulse sequences. Now, it is possible to enhance the sensitivity of spins with low gyromagnetic ratios, such as carbon-13 or nitrogen-15, by polarization transfer techniques such as inept from spins with high gyromagnetic ratios such as protons. Two-dimensional spectra can be obtained by measuring signals as a function of 2 time variables and transforming them by double Fourier transform into 2 frequency variables. The two-dimensional COSY and NOSY experiments reveal correlations between homonuclear pairs of spins. COSY allows one to identify scalar couplings or J-couplings, whereas NOSY allows one to map out dipolar couplings through the Overhauser effect. HSQC, which means heteronuclear single quantum correlation spectroscopy, can be used to reveal correlations between carbon-13 or nitrogen-15 on the one hand and protons on the other. Two-dimensional NMR experiments can be combined to produce three-dimensional NMR experiments.